40. As you guys, I guess, all know very well, phase 2 of the project is due tomorrow. We should be posting phase 3 probably later on tonight. We're just, working out a few kinks, making sure that it'll all go fairly smoothly. But definitely be on the lookout for that. We'll post on Piazza as soon as it's up and ready to go. Other than that, just logistics-wise, I will be out next Thursday, and so I will potentially be doing a tape ahead of that lecture on Tuesday. So just to maybe briefly take a poll and sort of see how well it might work, I'm thinking of doing that basically sort of over lunch on Tuesday, so something like 12 to 1:30. Does that work for sort of anybody in the room? Raise your hand if you could actually make it at that time. Tuesday, yes. So it would be like, basically it would be an hour break between the end of the lecture and when I would sort of do the tape ahead lecture. Is there another class at that time, or people just want to have lunch? So can anyone make it? Raise your hand if you can make it. Will make it? Okay, I see. So we'll again post on that on Piazza. Worst case, if we don't work that out, I'll get somebody to just come by on Thursday and take care of the lecture as well. Possibly. I'll take a look. So maybe actually what I'll do is, if anybody has a strong preference on doing it, let's say during lunch versus, let's say, the suggestion was later in the evening or maybe like after 4 p.m., just send me a note and let me know. But like I said, I'll need to check on the scheduling logistics and et cetera to make that happen. Okay, so. No, so, yeah, exactly. Now, it'll be a bonus lecture, and then you have, let's say, the penalty lecture on Thursday, which will not happen. So the net number of lectures will be the same. It's just basically taping ahead. Obviously, if you can't make it, the video will be available, a couple days after that. Okay, great. So last time we were basically talking about, we finished up with comparators, and then we started talking about mismatch, which, as we said in the beginning, was the source of what would actually cause offsets in the comparators. So before I sort of dive back into where we were in the lecture notes, were there any questions on that or the project or anything like that? You guys are all here, so you're well on your way in the project and therefore have no questions. Okay, so if not, let's go ahead and dive back into the material itself. So as I mentioned, last time we really started talking about what was going to cause mismatch in our transistors. And I believe where we basically ended up was saying that there's actually a few different types of mismatch that we might be interested in. The first is the so-called deterministic sources, which really just means that fundamentally there is actually a difference that should always repeatedly happen between those two transistors. And we said that a lot of those were related to things like, for example, the local environment around the devices not being the same, and so therefore that would cause, for example, the poly gates to be etched in a different way, or may cause different stresses, or there may be other various forms of lithographic interactions, and so on and so forth. So we said that if really we did a good job with the layouts, and I'll say some more about that a little bit later on in this lecture, but basically as long as we did a good job with the layouts, following similar techniques that we talked about way back in the beginning of the class, largely speaking, we should be able to make these deterministic sources very, very small. So what you're then really left with is these so-called random sources. We said these were things like just how many dopant atoms were actually sitting inside of the transistor channel. Because, again, that's done through some ion implementation process. If I've only got, let's say, 20, 30, 40, 50 of those atoms in total inside of a small transistor, then the presence or absence of one of those atoms makes a difference. And obviously, nobody builds a chip with, a billion plus transistors by counting how many atoms went into each and every single one of them. Okay? So this actually increasingly is one of the biggest sources of variation or mismatch that we'll be running into. But we said there's actually lots of others as well. There's the so-called line edge roughness, which just means you can never really draw things exactly the way you expect it to. So if a photon hit a particular point or not, again, would cause a slightly different shape to appear. And as we talked about a little bit in the context of 1 over F noise, if you looked inside of the oxide, there's oftentimes defects. And obviously those defects are random in nature. So again, that can cause basically random variations in the behaviors of the transistors. So as I said a second ago, we're really going to be focusing our modeling on these random variations, because we're going to try and make sure that all of the deterministic stuff we just take care of by following good layout practices. So I just wanted to mention a couple of the key references here, mostly because there was some really kind of seminal work that was done in this mismatch characterization and understanding space. And I should mention that mismatch is by no means a new problem. So if you look at this upper paper here that was basically written by mostly Marcel Pelgrim and some of his colleagues at what was Philips at the time. And by the way, this is one of the most referenced papers that are out there in the sort of overall community. This work was actually done back in 1989. So again, more than 20 years ago, this mismatch certainly not a new problem. So the real sort of key, let's say, innovation that was, or let's say, advancement that was described in this paper was first a model to actually predict how these random mismatches depend upon essentially your design of the devices. But second, also a lot of very detailed and careful measurements to actually validate that model. And as you can imagine, doing those measurements is pretty tricky, because if you're not really, really careful, any sort of small difference in your layout or anything like that could very easily swamp out the effects that you're looking for. Meaning you might actually be measuring deterministic effects rather than the truly random things that you're interested in. So again, this is a really, really good paper. I highly recommend people go and check this one out, because it really was the sort of setting the baseline for how people really still even now deal with and understand mismatch. Now, having said that, obviously, given that it was over 20 years ago, this was done with, I guess these days, what would be essentially an ancient technology. So this is 2.5 microns. So obviously the exact data numbers that are there don't really translate into what we would see today. So I'm mentioning this other, or I've listed this other paper here that was done by Willie Sanson's group and some of his colleagues, which gives you some more updated both models and data. For example, for a 0.18 micron CMOS process, there's actually been quite a few works that have followed up upon this, upon sort of the original Pelgrim paper. But as I said, really the Pelgrim paper is kind of the place to start from, because it really does lay out all of the basic principles. Okay, so before we dive into the exact details of that model, there's one thing that we just need to essentially kind of get out of the way. And that's that if we're going to really do this modeling of the random variations, then we need to kind of state really what our assumptions are going to end up being. And in particular, the most important assumption is just that we're going to be assuming that the total mismatch in any one given transistor is, of course, set by the composite of a lot of individual single events. And more importantly, that the sort of correlation distance, meaning the physical distance that over which each of those events would have an effect, is very, very small compared to the device dimensions. And this assumption here is really quite important, because this is kind of the only way that we can then actually come up with a model that would say, okay, well, if I have a bunch of these little small individual events, then I can just say that as long as their correlation distances are very small, then they really are indeed independent. And I can basically say that I'm just going to add them all up and essentially invoke central limit theorem and say that at the end of the day, my mismatch should just be some zero mean with a Gaussian distribution. Okay? And by the way, in case you're wondering, it typically is a pretty reasonable assumption to say that the correlation distance is small compared to the devices. Because as an example, as I said before, if you're talking about dopant atoms, you're literally talking about an individual atom. Okay, now maybe eventually we'll get transistors that are individual atoms. At least for now, we've still got, a reasonable number in there, and so that is indeed much, much smaller than the device dimensions. Now, again, just to make sure it's clear, this is just like noise in the sense of you cannot ask the question, in advance, what will be the mismatch between transistor A and transistor B. All you can make statements about is what the mean of that mismatch is, and what the standard deviation or variance of that mismatch will be, or really what the distribution of that mismatch will be. So again, throughout the rest of sort of this lecture and in fact the class, we're going to be assuming that the individual mismatch parameters we're looking at are all zero mean and with a Gaussian distribution. So now that we've gotten that out of the way, now we can really look at what will be our mathematical model for that mismatch. Oh, yes, question.
Is the correlation distance being smaller than transistors? Does that mean that random variations are going to be happening kind of over the size of the device?
Yes. So the question was, does this correlation distance being smaller than device dimensions mean that these random variations are kind of distributed throughout the entire device? And the answer is absolutely yes. And in fact, that's actually exactly why the equation that I'm going to show you right here is going to take the form that it does. Okay? So, if we take any general parameter, and this parameter could be the threshold voltage, it could be, for example, the mobility, it could be the drain current, and etc. At the end, what we're going to see is that the mismatch or the variance of the mismatch in that parameter is always going to be equal to some process-dependent constant, which we're just going to call AP, divided by the gate area of the device, plus some other process-dependent constant, times the distance between those two devices. Okay, now there's a couple points that I really want to emphasize here. The first is that when I notice that I explicitly said that this is the mismatch in that parameter. So when you quote this sort of variance here, it's always between pairs of devices. Okay, so you have to be very careful about that because you can get yourself very confused if you start using this as a single device. This is always between pairs of devices. The other sort of, let's say, points that I really want to mention here is that there's kind of these two terms here. One is this area-dependent term, which just says the larger that you make the device, the smaller the mismatch will be. And we'll see why that is in one more second. And the second says that the farther apart you make those devices, the larger their mismatch variance will be. Okay? So much like we had said in terms of doing, let's say, good layouts, this second term here, largely speaking, we're actually going to try and make be 0. In other words, we're going to try and make those devices essentially be right next to each other, or in fact, even on top of each other. Now, this may not be immediately obvious when you first think of it, but as we'll see a little bit later, you can actually do device layouts that would indeed make the quote-unquote distance between the devices 0. Okay, again, this sounds a little bit funny at first, but it is possible. So for most of the rest of the discussion, I'm not going to spend a lot of time on this term here. I'm mostly going to focus on this term, which is intrinsically related to the size of the device itself. And by the way, this WL here, that's really the gate area of the device. Okay? Now, you may be wondering, why is it that it's the gate area of the device that basically matters? Why is it that increasing that area decreases the mismatch? And the answer is pretty simple. So, as we said before, what we're kind of assuming is that these mismatch things are all individual random events. So let's just take the doping as an example. And of course, the doping would affect the threshold voltage. So if I drew the gate of the device, so that's kind of what this square is indicating here. And if I have some random sort of doping profile or distribution, then I can kind of fill in dots that would basically be, on this particular device, how many atoms or dopant atoms happen to actually make it inside of that particular area. Okay? So if I was to go and take another device that just had a larger area, and then apply the sort of same statistics of whether or not dopant atoms happen to be inside of it. So again, let's just sort of draw some picture. And of course, this is, again, random. As should hopefully be clear, if I'm really applying, let's say, the same statistics, because I have, in this, let's just say that this one ends up being, I don't know, double the area or 3 times the area, whatever it is, then if I looked at, let's say, the mean, the variation relative to the mean, right, what I'm really doing here is I'm averaging more of these random events out, right? So on average, I'm certainly going to have more things that sit inside of the box. But remember, the more I average, the better the mean to the variation ends up being. Yes?
I guess, conversely, it also seems like if you have bigger devices, they're by definition farther apart.
Okay. So you said it seems like if you have bigger devices, they're by definition farther apart. With this kind of picture that I'm showing you here, it would indeed seem to be that way. There's some tricks that we're going to play. Okay? And we'll see it in one second, but to zero order, you can imagine if I play some interleaving tricks, I can basically make it look as if the devices are right next to each other. It's a very good question, but we'll see it more a little bit later on. So does this make sense to everybody as to why increasing the area actually helps you decrease that mismatch? Yeah, and remember what doping concentration means is per unit area, on average, how many atoms would be sitting underneath that gate there. And so the average doping concentration is indeed the same. The trick is just that if I have a larger area, then I get to average out more of the individual small variations. So it's kind of like saying, if I took this box here and I fit it inside of here 2 or 3 times, then if this box had a certain sigma of variation, right, in terms of the number of atoms, this box would have basically 2 times that sigma in terms of variation. But the total number of atoms would be 4 times larger. So the relative variation would actually be half the size. Does that make sense? Or? Yeah. Okay, great. The same idea applies for resistors as well. Depends obviously on the exact mismatch mechanism, but this model is quite general. Yes, so it's quite general in terms of really being sensitive to the area of the structure or the device that you're interested in. The question, by the way, just to repeat for the online folks, was can you apply this to a resistor as well? And the answer is absolutely yes. Okay. Now, having said that, I do want to point out one thing which is much like to what we had seen with noise. So notice, if you want to get a factor of 2 improvement in the sigma of the matching, how much more area do you have to spend? So a factor of 2 in sigma. Yeah, it's 4x the area. Okay? So that means that if you're going to try and reduce the matching purely by brute force sizing, it's very expensive. Because if you want 2x in matching, 4x in area. 10x in matching, 100x in area. So as we'll see in 1 second, if you sort of just do the brute force approach, it very, very quickly becomes very expensive. Now, sometimes you have no choice. You just need to match things intrinsically that way. But as we'll talk about next week, a lot of times you actually prefer to apply something slightly more intelligent to get rid of the mismatch, simply because if you just do it the brute force way, it can indeed be very, very expensive. Make sense to everyone? Or? Okay. So what I'm going to do now is just walk through a few of the individual parameters that would actually be mismatched or that would actually track with this particular model that I'm talking about. And the first one that I'll spend a little bit of time on is actually the threshold voltage, because it turns out that in most of the circuits, especially in modern technologies that you're interested in, the threshold voltage mismatch tends to be the dominant factor in terms of setting the overall offset and et cetera of your structures. So again, this is really the mismatch in VT between 2 identical devices. And really all I did here was repeat the exact same equation, but just plugged in that there's now this AVT parameter, which is representing the level of mismatch as a function of the area of the device. Now, the units of this parameter, which I quoted in this 2.5 micron process, are typically in millivolts times micron. So this sounds initially like a little bit funny of a unit, but it is indeed correct, because if you pay attention here, what I'm basically trying to figure out is what's the variance in millivolts squared, normalized by the device area, which of course would be in micron or meters squared. Okay, so let's say the way to interpret this is to say that, as an example, in this 2.5 micron process, if I had an AVT of 30 millivolt micron, that would say that if you had a 1 micron squared device, meaning 1 micron wide by 1 micron long, it would have 30 millivolts sigma of mismatch. Okay? So now let me ask you guys, how should I sort of interpret that, or how should I use that if I'm interested in, for example, when I gave you the project and I said that the mismatch of the comparator was 20 millivolts, what do you think the relationship between that 20 millivolts number was and the actual sigma of the real circuit? How do you think I might have chosen that?
You want some fixed number of sigma to get a certain yield?
Yeah, exactly. What you basically want to decide is how many sigma do I want from the standpoint of ensuring that my overall circuit will have a given yield. And so, by the way, 3 sigma happens to be a very common choice because that translates into something like, I don't know, 99 point whatever percent yield. So just again, keep that in mind, because the sigma, once you've calculated it, the way you will then use it is by figuring out, well, how much of or what percentage of my chips do I actually want to get to be functional, given that there is this mismatch constraint or this mismatch issue. And again, very typical number is 3. Yes?
So you're saying like 3 sigma is about 9% that's just for one device though, right?
Okay, great question. So the question was, if I only use 3 sigma on that one device, isn't it just for that one device that I'm sort of guaranteeing that 99 point whatever percent yield? That's absolutely correct. As we'll talk about it a little bit later, if you do a slightly more complicated circuit, things are a little bit more interesting in that obviously each of those individual transistors or each of those pairs of transistors has its own mismatch. So what you might be interested in is the mismatch of the overall structure as opposed to just a pair of devices. Having said that, I'll be, let's say, describing a technique that will in some senses do an even worse approximation or an even worse assumption. So that if you really did 3 sigma on each individual pair of devices, that would actually be much worse than 3 sigma on the overall structure. And again, we'll see exactly the detail of that when we get there a little bit later on. But it's an excellent question. Other questions on this? Or? Okay. So by the way, this plot over here I believe is from the Pelgrim paper. It's just showing that indeed the model matches fairly well with the measurements. So what I'm showing you here is another measurement from that paper, which is just looking at, okay, so if I take those 2 transistors and I measure the threshold voltage, or really I measure the mismatch in threshold voltage between them, is there any dependence on that mismatch upon the bias I use across the transistors? So in particular, just to be clear, the experiment that's being done here is we're basically taking a pair of transistors, we're tying them to the same gate voltage, VGS, and to the same drain to source voltage, VDS. And what we're going to do is we're going to measure how does the mismatch in threshold change between these 2 transistors as you change the VDS. Now, as you can hopefully tell from this plot here, in this particular technology, changing the VDS didn't have too big of an impact on the mismatch in threshold between the 2 devices. The thresholds of each individual devices, of course, will change as you change the VDS, but the mismatch between them did not change in this particular example. So that's kind of good news, because it says that, as an example, you could just go and calculate this threshold mismatch at pretty much any drain bias or any reasonable drain bias, and it would give you pretty much the same answer no matter how you really used it in the circuit. The bad news, however, is that in a modern technology, this statement that I just made may not actually be true. So, anybody have an idea of why that might not be true? What's the sort of physical effect that may mess this up? Dibble. Okay, so now, the interesting question, however, is why does Dibble mess this up? Okay, so great. So you made an excellent guess, which was you guessed Dibble just because that's something that exists in short channel and not in long channel. So you're absolutely correct, but now I'm going to show you another effect, and we'll see maybe if we can figure out afterwards why Dibble actually does impact the mismatch. Okay? So this is now actually, again, within old technology, and this is actually a measurement done on individual transistors now. So pay attention, the y-axis there is not the sigma, it's actually the individual mismatch between specific pairs of transistors that were measured. Okay? So, what this experiment is showing here is that as you change, for example, the source to body bias, and just to be sure it's clear to everybody, let me again do our picture of a good old NMOS transistor. Right, so we have our source and our drain, our gate, of course, and this is our substrate. So again, we're basically just applying a body to source. So let's just call that VSB voltage. And what this plot is indeed showing you here is that as you change that source to body voltage, you actually see the mismatch between 2 individual transistors change. Okay? So, why in the world might this be happening? What could cause the mismatch between a pair of transistors to actually change as you change both of their source to body voltages together? And by the way, the picture I drew here of the transistors will happen to be useful for this, so that might be a little bit of a hint. Sure?
Why is it that some of the transistor pairs are mismatching more and the ones that mismatching less?
Because remember, these are just individual transistor pairs. So the question was, why is it that some of these pairs have more mismatch than others? Remember, what I'm doing here is I'm showing you individual samples from the mismatch distribution. So this individual sample happened to have a delta VT of 1 millivolt at 0 source to bulk and went down to, let's say, -0, as you increased it. This one happened to have -2 and went the other way, and this one happened to have -3, and so on and so forth. So these are just individual samples of pairs of transistors.
So if you compare is the effect of the trends are in opposite directions just depending on how you're comparing the two?
I see. So the question was, is the effect of the trend going one way or another depend upon how you make the comparison? The answer is no. It actually has a lot to do with why this effect exists in the first place. And we'll see that in 1 second. So you'll see once we draw the picture, you'll see that it's perfectly reasonable that in some cases it would go one direction and in others it would go the other direction. So by the way, why does source-to-body bias change the threshold in the first place? What happens? Body effect. Okay, yes, but what do you mean by, what exactly does that mean? What does body effect actually do?
Depending on the polarity of the voltage of the device.
By the way, this is reverse. This is all reverse bias. Okay, so why does applying a body effect actually change the threshold voltage? Or why does applying a source-to-body voltage change the threshold?
It's going to pull some charge that's under the gate.
So you said it pulls some charge that's under the gate. Let me just give you a little bit of a reminder that I think will maybe answer the question as to why this effect exists. Okay, so let's say I had no bias whatsoever, right? I would then have some depletion region under this gate here, okay? And let me just also remind you that the doping is random. So let me just draw some picture of where dopant atoms may happen to exist or not. And let me maybe do the sort of depletion region in a different color so it's easier to see. So let's say that's the depletion region under some nominal bias. And each of those, little red marks I made was some dopant atom. All right, so what happens to that depletion region when you apply reverse bias, meaning you apply some source-to-body voltage that causes the threshold to nominally go up? What happens? Yeah, the depletion region gets bigger, right? It does something like this. All right, so now you guys tell me, why is it that this could cause the mismatch to change? What's happening here? You do have more dopant atoms in the channel, but here's the real key question. Why does the mismatch change? And remember, mismatch means between two transistors next to each other.
Well, is it sort of similar to the idea of the area of the gates? Like if you change the area of the channel, the number of atoms you're averaging?
It is indeed true that the number of atoms you're averaging is different. That is indeed absolutely correct. So, and by the way, just to be totally clear again, I'm showing you here the individual pairs of devices, delta VT. I'm not showing you the sigmas. So I'm not doing any statistical averaging here. I'm only saying if I take two literally individual devices and I change their source-to-body voltage, I will see that their individual mismatches change. So why is that?
Is it because the size of the channel is slightly different?
Okay, that is possible. You said the sizes of the channels are slightly different. That is actually possible. Let's even ignore that. Let's just assume that this depletion region actually changes uniformly between the two transistors. Why do I claim that that could still cause the mismatch to change?
You said the dopant atoms are randomly distributed.
Yeah, exactly, right? The dopant atoms, they're just random. So even if I uniformly change the area between the two devices, depending upon how many atoms I happen to catch in device A versus how many atoms I happen to catch in device B, I'll get a different threshold. Okay? So indeed, that's really the fundamental, let's say, mechanism for causing this. It's just that the dopant atoms, you don't exactly know where they are. And if you just so happen to get lucky or unlucky, you'll catch some different number in device A versus device B. Yes?
If it's kind of a random effect, why is there a consistent trend?
So the actual doping distribution may not necessarily be perfectly random, although you can kind of see that, it's true that for some given device, it tends to move in one direction versus the other. It really depends on the pair of devices. And you can notice that for each sort of pair of devices, it moves in several different ways. Meaning that, for this pair it happens to be negative with a relatively shallow slope. For this pair it happens to be positive with a slightly higher slope. This pair it happens to be negative. And in fact, you can see this sort of non-monotonic here. So maybe don't pay too close of attention to the dotted lines, which are just the extrapolations. You can see that each data point actually has some wiggle and movement around it. Does that make sense? Or? Yeah, no, so the question was if you're just randomly including versus disincluding, it would be sort of totally all over the place. It's true, but remember, I am approximating somewhat because the real, let's say, depth of the depletion region actually depends upon the doping atoms as well, right? So it is slightly more complicated than I've explained, but it really just comes down to sort of randomly including or not including certain atoms and how that affects the threshold voltage? It's a very good question, though. All right, now that we've sort of seen that, can now you guys answer my earlier question about why might Dibble change this picture? Yeah, exactly. Dibble is all about changing the depletion region. So just like with the body effect, it's going to change how many atoms you picked up or not. And therefore, again, this picture may not be quite the same in modern technology where you have a lot of Dibble, meaning you unfortunately have to be a little bit careful with how you measure the mismatch as a function of the drain bias. Make sense to everyone? Or? Great. So we looked at the threshold voltage, and now we can start looking at, let's say, a more complex composite parameter. So as an example, I oftentimes might be interested in just if I took two transistors and I measured their drain current, I might be interested in how much do their drain currents vary relative to each other. And in particular, you'll typically take this as kind of a normalized measurement, so you're usually not interested in the absolute value of the mismatch in the current, but you're usually interested in the percentage mismatch in current. So what this plot is showing you here is that if you change the VGS of the device for a couple of different VDSs, you can see that as you increase the VGS, the relative mismatch in the current goes down. So now, you guys tell me, why might this happen? Why does this sort of make sense? Okay, you said larger VGS means there's more charge carrying stuff. That's absolutely correct. So maybe just as a reminder, back in the good old days, or in fact even now, what is ID sort of related to? What's it proportional to? Yeah, it's proportional to VGS minus VT, perhaps to some alpha factor, where alpha is maybe between 1 and 2. So now you guys tell me, why does it make perfect sense then that as you increase the VGS, the mismatch in current would go down? Yeah, exactly. It's less dependent on the VTH. And in particular, it's less dependent on the delta VTH. Because if I just add some fixed delta VTH term here, well, the bigger I make VGS, the less that, fixed number of millivolts of delta VT actually matters. Okay, so it makes perfect sense that the plot looks the way it does. Of course, also makes perfect sense that, the behavior in terms of current mismatch depends upon the bias point because, hey, after all, everything changes with the bias point. All right, so now here's another, let's say, interesting question or maybe observation to make. So if I make the VGS infinite, will the current mismatch go to 0 or not? Who thinks it'll go to 0? Who thinks not? Okay, good. Why not? What stops it from going to 0? Velocity saturation. It's true the devices will get into velocity sat at some point, although I'm not sure why that would make the mismatch not go to 0 or vice versa. So by the way, what other terms exist in this proportionality thing here? What else does the current depend upon? Okay, great. Depends on mu. You said it's VDS. Let's even ignore that for a second. We'll come back to it. Anything else? Okay, Cox. Anything else? W and L, exactly. All right, so notice all of those can actually vary. So if you recall, mobility actually depends upon the doping. We just said 2 seconds ago the doping is kind of random, so that's random. The oxide thickness, well, hey, the C-ox depends upon the oxide thickness, and so of course that has some variation on it. And in fact, as we said before, even the width and the length, you may think that it's 1 micron by 100 nanometers, but actually it could be something else. So all of those combined indeed will vary, so that these lines will flatten out. They won't actually go to 0. They'll be limited by some other source of variation, not just by that delta VTH. So most people like to sort of lump all of those other current variation factors into the so-called beta, or the current gain factor. So this beta is just used sort of, hopefully as you've seen in the classic equations, it basically just says ID is proportional to beta times something like VGS minus VT, or VGS minus VT squared, or whatever sort of normal drain current equation you like to use. So an example in the long channel device, this beta would be mu Cox W over L. But really it's just capturing all of the composite effects that basically change the relationship between, at a fixed gate to source voltage, how much current do you actually get out. So as you can see from the plot here, this also, largely speaking, varies with the area of the device. But it's a little bit more interesting in that that one is really comprised of several different physical sources of variation. And so because of that, it's actually interesting to think more carefully about exactly what would happen as we change the design of the device and in terms of how it would impact this beta mismatch. So as we said before, mobility is not actually going to be a constant. It's actually going to vary, for example, along with a dopant or along with other random defects that might be in the transistor. So if we want to calculate that overall beta mismatch, then indeed we're going to have to include the mobility variations. Similarly, as we said a second ago, the oxide thickness is not going to be perfect, right? So it's going to vary a little bit, and that will cause changes in Cox. Now, having said that, there is one piece of good news, which is this oxide thickness variation tends to be really, really small. And that's only because of the reason that these days there's some relatively small, like 2, 3, or 4-ish molecular layers that actually make up that oxide thickness. And so, if one is not there, that's a pretty big deal, right? That's pretty easy to notice. Okay? So in general, that oxide thickness really is very, very well controlled. It's not to say it's zero mismatch, but tends to be one of the most well-controlled parameters that are out there in the process. Finally, as we'd mentioned a little bit last time, we're always going to get edge roughness, which means that the W and L that you have are not actually what you had originally specified. So as an example, if you thought you drew the picture on the left, which again, if I was a little bit better of an artist, would have been perfectly straight lines, in reality, what you're going to get is something that looks more like this. Okay, so it's going to have these jagged edges to it. And so now with something like this, it's even sort of an interesting question as to, well, what is the quote-unquote width or length of that device? Because in any one sort of either horizontal or vertical cross-section, there is no unique width or length. Okay? So all of these are actually going to add up together to make our beta factor vary. So let's think about basically, if we wanted to again model that and figure out what would be the sources or what would be the overall model for that beta variation, this is sort of what I've written out here. So as we said from the get-go, if we're going to assume that each of these effects is independent of the other, then if we want to sort of come up with an overall model for the variance, then all we have to do is say that the variance of that beta is just going to be the sum of the variances of each of those individual effects. Now, by the way, I should also mention here, as I said before, you're typically most interested in sort of a normalized beta variation, meaning you don't care about beta in terms of, let's say, microamps per volt squared or whatever it is. You usually care more about a percentage variation relative to the nominal. So what I'm going to do is indeed figure out what this sigma squared of beta is, divided by beta squared, which is again just the normalized variance. I'm just going to add up the effects of each of these individual variation terms that we talked about a second ago. So for example, we said that the mobility varies, so I'm going to have some variation due to that. We said that the oxide thickness varies, so I'm going to include the variation due to that. And I'm also going to have, for example, each of the width and the length potentially varying, so I'll include the variances due to those. Okay? So these two hopefully are fairly sort of straightforward and obvious, but there's another actually very interesting effect that you get into with these width and length terms here. So to understand what might be happening there, we need to sort of again draw a little bit of a picture and maybe clarify what it is we really mean when we say width and length here. So let's say that indeed I just magically got lucky, and from whatever reason, these two edges of my transistor were perfect. Okay? But let's say that these two edges here, meaning the horizontal edges, actually have some variation in them. So if you really think about it, let's say I'm interested in figuring out what the actual length of that transistor is. And by the way, let's assume that the gate is oriented such that, what I marked there is the length, and the other one is the width. Okay? So, ignoring everything we said about mismatch, if I just gave you this, funny looking kind of transistor, and I asked you to tell me what was the effective length of that device, procedurally, what do you think you would do? Like, how would you go about either doing this in, let's say, a simulator or MATLAB, or even conceptually? Yeah, exactly. You'd basically carve this thing up into little subsections. Right? And if you made those subsections sufficiently small, then at each subsection you just measure its effective length, and then somehow average across the whole thing. Right? All right, so now if you think about that, as you increase the width, what should happen to the variation in length? It'll decrease, right? Because you're averaging more of those individual small subsections. Okay? So if you look at what's written down here, it's exactly saying that the variance in the length is inversely proportional to the width because of exactly this averaging effect. And hopefully, as you might not be too surprised, the reverse is also true. Meaning, if you make the device longer, its effective variation in width will be smaller. Right? Because then, to go back to this picture, instead of doing these vertical slices like this, you do the horizontal slices. Right? So the longer it is, the more of those horizontal slices you pick up. Okay? So, if we include these effects, we can then go in and, let's say, expand this beta variance equation a little bit. So first there's this distance term over here. Let's again just not worry about that for a second. We've got the mu term, which, as usual, will depend upon the gate area of the device. We've got the Cox term, which also will depend just upon the gate area of the device. But if you notice these width and length terms, notice they're not just dependent upon the gate area, but they actually have the other parameter in the denominator as well. So for example, the length variation depends upon WL squared, and the width variation actually depends upon W squared L. Okay? So the way to really sort of physically interpret this is that what's happening is that these individual dimensions really are sensitive to the edges. Okay? They're sensitive to the exact sort of, let's say, lithographic, occurrences on those edges. And so because of that, that's why you really are picking up sort of that other dimension in terms of the averaging. Okay? So to make sure that this is totally clear, let's do the following thought experiment. So as we said in the beginning, the way we were going to try and get smaller, or the only way we sort of had, at least from a brute force standpoint, to get smaller offsets, was just to increase the device area. Right? So clearly if you increase the area, this term just goes with the area, this term goes with the area. In fact, these are also somehow related to the area. But let me do the sort of following thought experiment of, there's obviously a lot of different ways one could increase the area. So one way, for example, would be to say, let's say I'll just make up a number. Let's say this is 100 nanometers. And this is, say, 2 microns. Okay, let's say that's sort of the total area that at some point I decided I wanted to use. So if I compare that device against the sort of composite device, which is now just a folded transistor, where each of those lengths is still 100 nanometers, but now the width is 1 micron. Okay? So if I compare these two things against each other, will they have the same mismatch in beta or not? Okay, so I see a couple people either shaking or nodding their heads, so let's just maybe get you guys to raise your hands. So who thinks it's the same mismatch? Different? Good. Which one's worse? Yeah, the 2-finger device is worse. Now, intuitively, why? So you said you have less averaging. It's true. Now, I guess the question is, in which dimension do you have less averaging? So why do you say that? Yeah, okay, so you said it's the W squared. That's correct. You do have less averaging in the width. But to say it maybe a different way, in which dimension do you now have extra edges? And by the way, I'm not saying that what you said earlier was incorrect. I'm only asking to make sure it's very clear. So in other words, how many edges were there in, let's say, the horizontal dimension and in the vertical dimension on this picture? There was only 2, right, in each of them. Well, notice here, right, I now actually have 4 edges. Okay, because vertically I sort of have this edge to this edge and that edge to that edge. And horizontally, of course, I have this edge to this edge and this edge to that edge. Now, having said that, because of the way this thing has been folded, meaning I actually kept the length of each individual line constant, you can kind of, once you, let's say, go through all the various factors of 2 that pop up, you will indeed see that it's actually this width term that changes. Okay, because if you sort of think about it in this dimension, I have to look at both this edge and this edge independently now. Okay? Whereas before, when I kind of folded them on top of each other, those things, they just went away because the whole structure was now continuous. Okay? So the point of all this is really just to say that you need to be a little bit careful in that you can kind of separate this whole thing into a couple of pieces. All right? This part here really is just purely proportional to the area. So any which way you change the area, that will get better. But this piece here, what it's really saying is that if you want to make sure that those terms are sufficiently small and they don't basically come back and bite you, you actually have to make both the width and the length individually large enough just to knock off those edge effects. Okay? So in other words, if you just, for example, increase the area by always leaving the gate length minimum and then just making the width larger and larger, you may not get the same kind of scaling as you had wanted. Meaning, you might be dominated by one of these 2 edge terms. Okay? So again, user beware, because if you don't keep track of that, you might do something sort of naive and get even worse than sort of the area scaling, right? You might have to do even more than 4x just to get a 2x reduction in the mismatch. So by the way, because of this, indeed, when you really want very, very good matching, you'll tend to use both widths and lengths that are much, much larger than the minimum of the technology. Just to, again, get rid of those terms right there. Make sense to everybody? Or?
So this only applies to edge reference, though, and not like other stuff that might come up with, like how the wells are laid out with the diffusion.
Okay, so you said this only applies to edge roughness versus the other things. There are going to be some other random effects that are kind of related to this in the sense of, if you think about some of those stress effects and etc., they are indeed dependent upon certain edges on the location of the structure. And so it is even actually slightly more complicated than this. So in other words, even this, let's say, mu parameter may not depend just upon the area of the device. It may even depend upon some of the exact edge characteristics. So in general, you really do have to be careful in that if you sort of look at the, let's say, mismatch characteristics, you may see that there really is a very different scaling for let's say, short channel or narrow devices as opposed to long and wide devices. It's not to say you can't do it. It's just you really have to double check all the mismatch parameters because they may actually vary along with those dimensions. Is that clear? Okay, no problem. Okay. So, just to kind of quickly mention a couple of other things that I think we've seen before, but we'll go through quickly here. So one is, as we talked about a long, long time ago, in the silicon IC world is not isotropic. So, in other words, what I mean by that is, if you have a transistor with current flowing, for example, from left to right, that is absolutely not the same as a transistor with current flowing from top to bottom. In fact, even right to left is not the same as left to right, and bottom to top is not the same as top to bottom. Okay? So all this plot here is showing is that indeed, if you compared mismatch between a device where, for example, its current was flowing like this versus like that, you'll see a much, much larger mismatch than 2 devices where the current is flowing in the same direction. For those of you guys who like, let's say, solid state physics or material science and all that, the crystallographic directions are not the same in these things. And so therefore the mobilities are not the same, and therefore also all of the mismatch effects are not the same. So really the take-home message here is, as we had said a long, long time ago, if you care about doing any kind of matching, the current flow directions have to be exactly the same. And one of the sort of techniques that I'd mentioned back then, just as a reminder, was essentially to make it so that all of your unit cells actually had current flowing in, as an example, at least two directions. So an example, if this was sort of your unit cell transistor, then you'd have, as an example, one of the currents flowing there, the other current flowing there, and then as long as you don't take this thing and rotate it by 90 degrees, you're basically really safe in terms of copying it. Because you know you've got current in both directions always, so you really can't mess it up. Okay? Except, for, of course, if you rotate it by 90 degrees. That's the only bad thing you can do.
So if you had a square gate, the same thing.
Square gate. So when you say square gate, what do you mean? You just mean like the L and the W are the same? Oh, it's the same issue in that it's really a question of where the drain contacts are. So let's say that indeed that was my transistor, but I had drain and source contacts to be precise, and those are my contacts, then current is flowing in one particular direction or the other.
No, what I meant is like going back to what you said about the orientation.
Uh-huh.
How it's dependent on your orientation because of the crystal.
Directions, right?
So if your gate is actually square, does the same thing happen?
Yeah, but notice, even if my gate is relatively square like this picture, if I apply a drain to source voltage, for example, this is the drain and that's the source, then I will have current flowing from the drain to the source. In other words, the current is all flowing in that one plane. Right? It's not, I mean, okay, you could argue that maybe some electron happens to, sort of bounce and move in some other direction, but in bulk, they're all moving in one direction. Right? The current is all from right to left. Right? Is that clear? Okay, great. Okay, so that's one sort of just point to, again, this is one of these things, just don't mess it up. If you mess it up, then you're in trouble. The other thing, as we had said before, was this so-called distance effect, which is this is really just a plot kind of verifying the equation we had before, which was to say, if you increase the distance between the devices, the matching got worse. Okay, so of course the answer is, well, as usual, if you go to the doctor and you say, oh, every time I do X, it hurts, the doctor says, well, don't do it. Okay, so same thing here. Don't put the transistors far apart. Keep them as close as you absolutely can. Okay. Well, and again, we'll come back a little bit later as to how you can even be a little bit more clever to really enforce that would happen. So the last thing that I want to sort of mention briefly before we move on to actually do a couple of examples as how you might use some of these calculations is to say a little bit about how the mismatch actually changes with the process technology. So there's kind of, let's say, both good and bad news from this standpoint. And by the way, here I'm going to focus really on AVT, but you can actually do some similar, let's say, thought experiments with other of the parameters as well. And by the way, AVT is, of course, the threshold mismatch. So as you can kind of see on this plot, by the way, this plot is just showing you what the gate oxide thickness is. So as you decrease that gate oxide, which implies, of course, that you're going to a more modern technology, you can see that indeed this AVT actually does become smaller. Now this is perhaps not too surprising because as you shrink that oxide thickness, effectively for sort of the same amount of, let's say, doping variation, the relative change in the threshold goes down. Okay? So of course this also depends on the exact doping levels you're using in the first place, but to zero order, the good news is that AVT does tend to scale along with technology. So I'd mentioned what those AVTs were back in 2.5 micron or so. This is actually just some plots, I believe, from the Sanson paper, showing you roughly what the AVT is, as an example, in a more modern technology, which is the 0.18 micron CMOS. So in this particular technology, and I don't remember if this is exactly what these plots show, but a typical, let's say, AVT in 0.18 micron would be something like 8 millivolts times micron. So now, let me ask you guys, in our 90 nanometer technology, given that the AVT sort of scales along with the oxide thickness, what do you think the AVT will be in 90 nanometers? If only it was that good. So you said 2 millivolt micron. Unfortunately, it's not quite that good. So it's only a linear scaling. So what does it end up being? It's 4 millivolt micron. Okay, so by the way, just maybe to make it clear, the AVT is literally proportional to Tox. And at least in, let's say, standard scaling, the oxide thickness would just go linearly along with the lithographic dimensions. All right, so it turns out there's, let's say, some good and some bad news here. So the good news is that AVT indeed goes down with the technology, right? That's good. That's certainly no reason why that's a bad thing. The only problem, however, is that unfortunately this AVT might not actually be going down fast enough. So to explain why I say that, let's just do again another sort of simple thought experiment. So let's say that I'm interested in what is going to be the threshold mismatch of the minimum size device in a given technology. So you guys tell me. And by the way, of course, to figure this out, what we have to do is look at both the AVT and the W over L. Okay, so remember the sigma squared of the VTH is going to be equal to that AVT divided by, AVT squared, excuse me, divided by WL. So now you guys tell me, what happens to that as technology changes? So let's just say, by the way, I went from technology 1 to technology 2 with a scale factor of S, where S is less than 1. Ah, so is it? So let's see. AVT squared, what did we just say that does? Oh, by the way, S is less than 1 in this particular example. S is just the scale factor. So for example, from here to here, S is a half. Okay? So what does AVT squared do? S squared. Okay? What does W over L do? Excuse me, W times L. Ah, is it S? It's S squared. Both the width and the length would scale, right? So now you guys tell me, what happens to the sigma squared of VT? It's constant, doesn't change. So now, is that good news or bad news? Yeah, so if the absolute voltage went down and the sigma squared of the variation stayed the same, that's bad news, right? Because now, for example, if you're doing some, let's say SRAM design or something else where you really care about VDD minus VT, well, yeah, really bad news, because very quickly that mismatch becomes a huge deal. Okay? If, on the other hand, you actually only cared about exactly the mismatch itself, meaning in absolute millivolts, and everything else you were dealing with was constant in absolute millivolts, well, okay, I guess life's not really any worse, right? It's basically kind of the same thing, right? Meaning there's the same relative device area you have to spend to get a certain level of mismatch. Okay? Make sense to everybody? Or? All right, so as I said before, now let's think a little bit about how we might use this, let's say, in a specific calculation that you'd be interested in. And it's not that I'm going to be using, let's say, exactly calculating numbers or anything like that, but this is really more from a design standpoint. What are the things that we can do to improve the behavior of our matching? So let's first start out by, again, sort of doing this current matching. And to be clear, I'm essentially going to be taking a current mirror and asking the question of how well will the bias current, for example, on this side, match with the bias current on this side. Okay, and let's not worry about things like Dibble and etc. for now. So the way I can sort of execute this calculation is just to say, well, okay, there's going to be a mismatch in the threshold, which let's just call that delta VTH, which I can, of course, model as I've drawn there. And there will also be some mismatch in the beta. And if you kind of think about it, the easiest way, let's say, at least from an analytical or conceptual standpoint, to think about a beta mismatch is to say that if my original device had a certain, let's say, beta associated with it, it's almost like I'm taking another transistor with a so-called delta beta and putting it in parallel with the original device. And so I'm abusing terminology a little bit here in that, betas are not really widths. But if I lumped all of that effect into the width, then this would be a good model, right? Yes?
Are we interested in, CLM in this case here?
I'm not going to worry about Dibble or channel length modulation or anything like that. I'm really just worried about the effects due to the beta mismatch and the delta VTH mismatch. Okay, so now you guys tell me, what will be the delta ID between I1 and I2, meaning what's the mismatch in I2 and I1 given this particular setup. And there's one term that should be basically like completely obvious, and there's another term that you have to do a little bit of manipulation to get. So by the way, again, to be clear, if I told you that the gate voltage of these two transistors was the same, but this device was 10% larger than that device, how would the currents mismatch?
Delta beta times something.
Okay, delta beta times something. Let's see if we can figure out the something. So, and by the way, let's just assume that I'm interested in the normalized mismatch for a second. So if this is 10% larger than this guy, how much is the normalized current mismatch just due to that?
Delta beta over beta.
Yeah, so 10%. Okay, so indeed, there's a delta beta over beta. And if we want to figure out what do we multiply that by? If we're interested in the absolute value. Yeah, just by ID. Okay, so that's one term. And by the way, I'm still going to be applying the linear superposition here. So I'm going to assume that each of the individual mismatch effects is small. So I'm not going to worry about, cross-coupling and things like that. So what's the other thing that I need to add in? Okay, you're right. There's going to be some VGS minus VTH. What's our usual, let's say, small signal way of dealing with small voltage changes? There we go. Just GM times delta VTH. Right? So as long as that delta VTH is sufficiently small, I can just model the error in the current as just being GM times delta VTH. All right, so now if you recall, I said that I typically am interested in the normalized current mismatch, meaning delta ID over ID, as opposed to just delta ID. So I'm just going to divide everything out by ID, which of course is going to give me delta beta over beta plus GM over ID times delta VTH. Now, hopefully you guys have seen this particular one enough times that you know what I'm going to be looking for here. But can I simplify this any further? There we go. Put in a V star over there. Now, by the way, there's a factor of 2 you have to be careful of because GM over ID is not exactly V star. It turns out to be 2 over V star. But indeed, I'm just going to do exactly that replacement. It's going to be delta beta over beta plus 2 over V star times VTH. Okay? Yes?
Can we be adding these invariants?
Oh, okay. Yeah, I'm going to do that in 1 second. So here I've assumed everything is sort of deterministic. But now, to get to your point, the question was, should you be doing this in variance? Given sort of everything we just did, if I'm interested indeed in the sigma squared of delta ID over ID, that's going to be equal to A beta squared divided by WL plus 4 over V star squared times A VTH squared. And I'm sorry, I lost a delta here, divided by WL. Okay, so indeed, when you did it all in variances, now this variance equation that I wrote is totally accurate. I'm abusing the notation slightly in the pictures in the equations above, but they're really just to get you to this point. Does this make sense to everybody? Or? All right, now, perhaps not too surprisingly, what does this tell you about how you want to choose V star if you want good current matching? Yeah, you want big V star, right? Because the bigger the V star is, the less sensitive you'll be to this delta VTH term. And in other words, if you have a big V star, as we said, even actually several slides ago, just knocks off any threshold mismatch. And by the way, this should again actually be not too surprising because if you remember, we said when we're interested in noise, you also want a large V star. You can think of offset as just being DC noise. Okay, so same exact concept applies. Now, having said that, there is one thing we have to be a little bit careful of, perhaps maybe actually 2 things. But what's perhaps bad about increasing V star in this context? Yeah, there we go. Okay, so remember, changing the V star for a fixed bias current will actually change the width and perhaps the length depending upon how you've set the problem up. Okay, so the thing you just do have to be a little bit careful of here is that as you increase that V star, if you're trying to fix the bias current, the width and the length will actually, or the area will actually go down. So it turns out that in most technologies, if you sort of do a plot of minimizing the mismatch, for example, versus V star, you may find that there's actually an optimum point. Okay, because there is a trade-off there between increasing the V star to knock off this delta VTH term, but at the same time, it may reduce the W over L, the W times L, sufficiently that the curve sort of goes back up. Okay? Make sense to everybody? Or? All right. Let's repeat the same thought experiment now, but instead of being interested in current matching, now let's say that I'm looking at something like, for example, your comparator, and I want to know what's really going to be that input referred offset voltage, at least in terms of the sigma or the variance of that design. And so let's just, abstract things again to something simple. Let me give myself a little bit more space. So let's just say that at the end, all of that mismatch is dominated, for example, by the mismatch in my input differential pair. And again, I'm interested in what's the voltage offset that's going to be caused. So just like before, I can sort of at least conceptually model it as I have some delta VTH as a voltage source at the input. And similarly, if I had some beta, I'm going to have an additional delta beta on one side. And so again, the question I'm going to be asking is, given this setup, what would be my offset, my differential offset voltage? All right, so by the way, just like before, there's one term here that should be really, really simple and obvious, and there's another one that you have to manipulate a little bit. So what should be the immediately obvious one in terms of the voltage offset of this differential pair? And by the way, voltage offset, I really mean at the input. Yeah, there we go. So there's a delta VTH. Okay, now there's so we got rid of that. So now we just have to include the effect of the current. So how are we going to translate the delta in current into an offset in voltage at the input? Yeah, divided by GM. Okay, so just like before, if we want to know how much current mismatch we had, that's just delta beta over beta times ID. But now, because we want to bring it back to an input voltage, we'll just divide it by GM. All right, well, so again, hopefully this trick has become blindingly obvious to you guys by now. I will once again invoke V star. So that we'll just rewrite this to be delta VTH plus delta beta over beta times V star over 2. Okay, and so as with before, if we then look at this a little bit more carefully and really think about what it implies in terms of the variances, it says that the sigma squared of my offset voltage will be equal to A VTH squared divided by WL plus A beta squared over WL times V star squared over 4. All right, so now again, perhaps not too surprisingly, what does this say about the V star that you want to use? You want it to be big or small? Yeah, you want a small V star. Right? Smaller the V star you use, the less you're sensitive to this A beta term. Again, with the caveat of, you have to be careful about device sizing and things like that. Does this make sense to everybody? Or? Yeah, okay. So here it does actually help you, although that's correct. Everything sort of goes in, let's say, the right direction here. But remember that there are other reasons why you may not want that small of a V star. Right? So there's capacitive loading, there's power, and etc. Right? So it is true that in this particular case, that happens to help you. But once again, you have to be a little bit careful with, just blindly making everything really, really big. It is true, however, that this one really has more of a sort of this optimization that you have to do. Whereas here, it is true that if all you cared about was DC effects, your best bet is indeed always to just make the V star as small as you can make it. Is this clear to everybody? Or? Okay, great. So just to make sure that we get to it, because it will be useful for phase 2 of the project, I'm gonna skip over the layout piece just for 1 second. If we have time, we'll come back to it. And so what I want to do is just briefly mention a little bit about how both, let's say industry or in practice, you might, what are some of the tools available to do simulations of mismatch? But more importantly, what's the method that I actually use by far the most often? Okay? So it turns out there's a lot of, let's say, tools that have been built into various forms of simulators to try and get you some estimates of what the mismatch behaviors will look like. So as an example, let's say that you wanted to repeat this same experiment we had done before. So you just take, for example, a differential pair, and you wanted to know what its input referred offset was. Okay, so we know that at the end of the day, this should really end up looking like, if I plotted essentially my offset, and I plotted, let's say, the probability distribution function, or probability density function of that offset, I'd have something that, as an example, would maybe look like this. Okay? Now remember, unfortunately, PDFs are sort of infinite things, right? I need to sort of have every single possible combination of offset and etc. to actually compute a PDF. So the only thing you can actually really do in SPICE, at least if you want to, have literally a matching to this, is to do what's called Monte Carlo. Okay, so the idea here is literally HSPICE just throws the dice. So for each, let's say, simulation run, it picks from some distribution it knows of for example, the threshold voltage offset, the beta offset, and etc. It just picks some value from that distribution, plugs it into the circuit, runs a simulation, and measures the offset voltage. And then if you do this, for example, let's say a quote-unquote 100 runs or 100 seeds, it'll just do that picking procedure 100 times. And at the end, what it'll usually come back and give you is something that sort of looks like this. So it'll give you a plot of something like how often did you see V offsets within a certain bin. Okay, so the x-axis is usually something like the number of hits. And it might look like something, for example, let's say like this. Okay, and by the way, I intentionally made it so that this looks kind of discontinuous here. So the warning that I wanted to give you guys is you have to be really, really careful with something like this. Because remember, you're only running some finite number of samples from some potentially very large and could be very weird distribution. Okay? So it's very, very common for you to see things like this where it's discontinuous and moves up and down and all these other things. You should not interpret this as being the real PDF of the actual parameter you're interested in. Because unless you do an exceedingly large number of simulations, it's highly unlikely that you sampled this space well enough to actually give you very good information about it. Okay? So when and if you use these kinds of tools, the only things you should really trust are 1, the mean. Okay? Because that's, that one, indeed, all of your samples give you very good information about the mean. And 2, but actually already to a lesser extent, is maybe just the sigma. In other words, just the variance. But even that is already starting to be more questionable unless you've really done a very good job of, doing enough simulations and etc. Does this make sense to everybody? Or? All right, so given this difficulty, it turns out that the way I actually almost always simulate the mismatch, and by the way, I think I can count on one hand the number of times I've actually run a Monte Carlo simulation, is to do the following. So the first step that I take in quote-unquote simulating the mismatch is to do absolutely no simulation at all and calculate it. Okay? Because it turns out that it's almost always easier to just do the calculation by hand, at least to get a first rough estimate, than it is to get any trustworthy result out of the simulator. So the very first thing I do is literally I just look at the circuit and calculate what the mismatch should be. Okay? Once I've done that, then I will actually start doing a simulation. But just to be absolutely clear, that simulation is only for verification. Right? It's just really to check that the hand calculation I did makes sense. All right? Now, what's the actual sim that I do? Well, I just do the following. I basically just say, well, as we had mentioned before, there's a certain desired yield. As an example, 3 sigma, right? And then if I want to model the behavior of my circuit under these mismatch, I just add in those mismatch sources directly, or deterministically, let's say. So to be clear as to what I mean by that, let's again go back to this differential pair example. If I have that diff pair and I went and I said, okay, you know what? I know my AVT, I know my A beta. The mismatch should be, as an example, a sigma of 10 millivolts in terms of the threshold offset. So if I want to then go and check how my circuit behaves, I will just literally go and add an offset voltage of 30 millivolts, which again is just 3 sigma of the offset that I calculated. Okay? And I will do this for each and every single pair of transistors in my overall global circuit. And then based upon that, that's how I'll, for example, calculate the overall offset of, let's say, my comparator or my amplifier or whatever it is. Okay? Now notice, if I add 3 sigma offset to every single pair of transistors, that's actually very pessimistic. Right? Because I'm doing 3 sigma on each individual pair. Whereas the net circuit would only have, to get a 3 sigma event, that's individual combinations of much smaller sigma on each individual pair of devices. Right? So I admit this is a very pessimistic way of doing things, because I'm really pushing the circuit. The more complex the circuit, the more pessimistic you're being. But the good news is, the reason why I always do this is, if I work with this, if I meet all my specs with this, I'm guaranteed to be good. Right? And I much prefer to get things that work and are guaranteed to be good than things that, may marginally work or not, depending upon, exactly how good I was at really setting up the precise, exact simulation. This make sense to everybody, or? Yes?
So if you're in a situation where perhaps, you have a very large number of transistors and this gets to be overly pessimistic, is there a rule of thumb for how you can sort of scale down the mismatch?
Okay, so that was a great question. So the question was, let's say I give you some really, really complicated circuit, and it now becomes complicated enough that, it becomes exceedingly pessimistic to add this in deterministically 3 sigma on every single pair. So the question was, well, is there some kind of rule of thumb of how many sigma should you use on each individual pair to kind of get a good estimate, so to speak? The short answer is that yes and no. So the technical issue is that obviously the sensitivity from each pair may be very, very different. And so unless you know what those sensitivities are, you have to be really careful with how many sigma you assign to each one of those things. Having said that, the good news is that oftentimes, just if you look at it from, let's say, an intuition standpoint, you usually know pretty well what the most important things actually are. So as an example, in the comparator, guess what? It's usually the input devices of the cross-coupled pair, right? And there may be a bunch of other kind of junk around it, but usually that's not sort of the dominant effects, right? So this is exactly an example where you just sort of have to apply a little bit of circuit intuition and knowledge to at least guess as to what the really sensitive parameters are. And then, you'll put in the 3 sigma on those, and then, again, maybe that's a little bit pessimistic, but that's usually there's usually only a couple of things that really are the dominant effects. But it's an excellent question. By the way, you can even do a circuit analysis to guess what the sensitivities are, and then based upon that, do a little bit more intelligent, mapping of how many sigma you use in each place. It's a great question. Okay, other questions on this, or? Okay, so if not, let me just sort of briefly intro the layout piece of it, and then we'll just wrap that up on Tuesday. So, if you guys recall, I'd mentioned even way back in the beginning of the class, when it really comes to layout and doing layout that's good for matching, it unfortunately turns out that just about everything that you can think of, and in fact things that you didn't think of, will actually change your matching parameters. So as an example, even if you just took 2 transistors that otherwise are completely identical and put a piece of metal, let's say metal 1 or metal 2 above them or not, guess what? It will change the matching characteristics. Okay, you'd think that this would have no effect whatsoever, because how in the world does the presence of the metal above it change, for example, the dopant ions and things like that? Well, turns out it does. If you're interested, there's something about, hydrogen bonds that are dangling or not. I don't even know. Believe me, it makes an effect. Okay? So, as we had said, way back in the beginning, what's the number one most important rule to follow if you want things to match? Yeah, well, okay, so when you say match everything, let's be more, let's say, specific. Yeah, everything has to be exactly the same. So the key word I like here is exactly. And when I say exactly, I mean exactly. Okay, so, any little small thing that may be slightly different, to the extent that you can make it the same, you're better. Okay, and you really have to be quite paranoid about this because, as I mentioned way back a while ago, people really like to focus on sort of one side of things or the other. So as an example, they may have two transistors that indeed are right next to each other, and I apologize for the bad drawing. Let's assume they were the same actual dimensions. They may say, well, okay, I've got one transistor here, and let's say a wire like this, and I have another wire like that. Well, sorry, those are not exactly the same. Okay? Because one wire is above it, and the other wire is below the thing. Okay? And believe me, that can be different. So again, if you want them to be exactly the same, better make sure there's a wire up above here and another wire down below there, even if those wires serve absolutely no functional purpose other than just matching. So again, I really want to emphasize the key word here is exactly. And exactly means everything around the device really has to be absolutely identical in every which possible way you can think of to make it identical. Make sense to everybody, or? All right, so unless there's more questions on that, we'll finish up next time. Oh, yeah, quick question.
The thing about doing all of this is it probably is going to hurt you quite a bit in area.
Ah.
How do you know when to
Stop.
take the time to do all of this, go to that effort?
Ah, okay, good question. So the question was, if you're really doing something like this, if you're not, well, depending upon what exactly it is, it could very easily sort of cost you A, some extra area, but B, perhaps some extra time in terms of doing the design. And so the question was, when do you sort of decide how much extra time to really spend in terms of really getting this absolutely right? So the answer is actually quite simple. It all depends on how much matching you care about. So if I'm building, let's say, a 2 or 3-bit DAC, and I literally don't care about, multiple millivolts or tens of millivolts of offset, I probably don't care, right? If I'm building a, let's say, 8, 10, 11, 12, etc. bits, well, sorry, you care. Okay, so you better really spend the time to get it right. Now, there's some magic line there. I jumped from 2 to 8. Where that magic line is, debatable. But roughly speaking, especially once you kind of get this concept ingrained, doing it right the first time actually becomes pretty easy. Because it's very, you're so heavily constrained that there's kind of, there's only really 1 or 2 ways to actually do it right. It's a very good question, though. Okay.